Today we are going to see the 2D problem, start up the two-dimension problem. So basically the idea of this part is to just give an overview of the type of 2D problem we are going to do, the various steps, and what are the basic fundamentals which need to be keeping in mind before going for numerical cases. Okay, so let's start with a simple two-dimension plate geometry. So let's say I have a plate, and to plate, give it a feel of plate. I'll draw the thickness also. Okay, and then this is the fill part. Okay, and then this is Lx and this is Ly, and the thickness is T, and this is basically solid. Okay, so in classical cases, the information which we have generally, the geometrical information, means we have Lx, Ly and thickness. Then we have the material data. Material data means, let's say, Young's modulus and Poisson's ratio, or density also, but in this case density has no role to play. So basically these are the information which we have. From this information, the objective would be to find out the, let's say, the displacement, elemental stresses, and principal stresses. Okay, so from given information in the form of geometric and material data, find out the displacements, elemental stresses and principal stresses and their directions. Okay, so let's move forward and see how we can do this. So basically, if I go downstairs, so in 2D cases, this two-dimension plate element has to be discretized. When I say discretize, it means identification of the segments. So this particular plate element can be discretized into different ways. So basically there are two basic element type. One we call this a triangular element, and second one is called rectangular element. So in triangular element you have node 1, node 2, node 3, and rectangular element you have node 1, node 2, node 3 and node 4. Okay, so in our case here we will call this triangular element as CST. CST means constant strain triangle. Okay, constant strain triangle. So on the very first few cases we will consider only this constant strain triangle for numerical solutions. So let's start doing the very fundamental step of 2D case. So let's say I have this, again I'm redrawing that plate element. Okay, I have a plate element, it has some thickness. Okay, now I have to discretize this plate element, so I take this is same geometry and then I partition into two parts. So this is my element number 1, this is my element number 2. So if I denote numbering, so first element number 1, this is 1. Okay, let's not mess up numbering time. So this is 1, this is 2, this is 3, taking counterclockwise. Okay, and then for second element, 1 already denoted 1, and this will be second one, and element 1 finish at 3, so it be number 4. Okay, so basically we have two triangular element 1 and element 2. Element 1 has degree of freedom 1, not degree of freedom but node 1, node 2 and node 3, and element 2 has node 1, node 4 and node 2. Okay, and this node, because we are dealing with 2-dimension problem, so every node has 2 degree of freedom. 2 degree of freedom, it means displacement in x. Okay, and then displacement in y direction. Okay, so in this way you can also, let's say, write here we will have ux. Okay, or I'll not say ux, but I'll say u1 v1, and then here you have u4 v4, here you have u2 v2, here you have u3 v3. So these are nodal degree of freedom. Okay, so taking this node information, a nodal degree of freedom, how we compute the nodal displacement, and that nodal displacement will give the elemental stresses and the principal stresses and their respective directions. So again, going back to basic fundamental, how we solve the finite element problem. So basically the basic procedure about the same. You found out the local stiffness matrix, local K, and then you have to assemble into global K. Once you have global K, then you formulate equation Ku is equal to F, then apply boundary condition, and then solve the equation. Once you solve the equation, then post process means finding out the to say stress and whatever information you wanted to extract from this. So it can be noted that in 2D cases, almost 60% of your work will be on finding out the local stiffness matrices. Once you have local stiffness matrix, then you can do the formulation of global stiffness matrices and then form the equation, apply boundary conditions, solve equation, and post process. So here we are going to explain only how we come to this local stiffness matrix. Okay, so if considering the same problem which we had, if I had say two elements, okay, element number 1 and element number 2, the node were 1, 2, 3, 4. If I take this part, let's take it out here, and I'll redraw again only this in zoom scale. Okay, so this is your 1, this is 2, and this is 3. Now you keep in mind that for 2D cases, node number 1 will be, say, geometrical starting point. It means at node 1 we have something 0, 0. Okay, and then other nodes are in respective form. Okay, so in this case we have to find out the coordinate information at every node. Coordinate means x and y values. So we know that in x direction this is x value, and in y direction this is y value. Okay, so we have to find out x1, y1, okay, x2, y2, and x3, y3. For the sake of simplicity and how books are considering, so this 1 can be also denoted at I, and 2 can be denoted at J, and this can be denoted at M. So basically finding out the xi, yi, okay, xj, yj, on xm, ym. And this is actually very simple because x means, let's say, this information lx, and ly information you already have. Okay, so for node number 1 this will be something 0, 0 because it's starting point, and then node number 2 will be what, lx and ly, because you travel x distance and ly distance. And for node number 3 you have something called x, you're not moving, so let's say you have 0, and ly you are moving, so this is 0 ly. Okay, so this geometrical information or geometrical coordinate for this particular element is very much required for forming the local stiffness matrices. This is just a prelim, and how and where we are going to use this prelim. So what we are going to do, I'm going to write a specific expression for the local stiffness matrices, and this is kind of, say, derivation, but in this case we are not going to derive it, but in the later at the end, if time permit, then we can derive in future lectures. So let's find out or write the expression for local stiffness matrix. Local stiffness matrix, let's say here we have this element. Okay, so the formula of this would be T A B transpose D and then B. Okay, so this is your local stiffness matrix formula. Here T means thickness of plate, A is area, B is known as gradient matrix, and this gradient matrix is a function of element coordinate system. And then you have D we call it stress strain matrix, and this stress strain matrix is a function of, say, material parameter. Okay, so see, this local stiffness matrix require all the information. Thickness, this is your geometrical information. Area from geometrical information. This gradient matrix from elemental coordinate. So for elemental coordinates, again you need this geometrical information, and then at the end stress strain matrix at, let's say, material properties. Okay, so now how we compute for this thing. So first case, this T you can directly compute from this thickness you find out. See, this is already given. So basically first parameter thickness you can directly compute. Okay, and then area of the plate would be half B into H. Okay, so T you can directly compute. Area will be half breadth into height, and then you have to find out this B matrix. Okay, and that B matrix is little bit, I would not say tricky, but you have to work upon it. So the explicit formula for this B means gradient matrix is 1/2 into area, and then you have this matrix and some information inside the matrix, and those information are, let's say, beta I 0, beta J 0, beta M 0, and then 0, gamma I 0, gamma J 0, gamma M, and then you combine both. So gamma I, beta I, gamma J, beta J, and gamma M, beta M. Okay, so say this is the explicit equation. In here, this A you can compute from here, and then this, actually you need only this information. This matrix has only BI, BJ, and BM, and gamma I, gamma J, and gamma M. And it's actually very simple. Simple means do not get trapped into this notation IJM. So basically this I, J, M are these three nodes. Okay, and this gamma and beta has a specific relationship. When I say specific relationship, it means it is relationship of the relationship of the coordinate information, element coordinate information, because we have already seen that this element coordinate system. So this is coming from this. So when we will do the numerical, then we will explicitly write the expression for beta, gamma, because this is actually known information. It's coming from a derivation, and this is standard. You need not, it does not depends on the any other information, only on the, say, coordinate. Okay, then at last one we call it D is a stress strain relationship. So D is coming as E by 1 minus nu square. This is nu, and this is, let's say, gamma, and then you have 1 nu 0, nu 1 0 0 0 1 minus nu by 2. Okay, and here in this matrix, this is this Poisson's ratio, and this E is Young's modulus. Okay, and this is again the same information here. Okay, so you have this. Okay, so if we go a little bit top, so basically we have T, this expression, A, cross section area, and then B, you can find out this is transpose, nothing magical, it's only the transpose of that matrix. This is transpose. Once we have B transpose, and then you have D from here. Okay, once you have this information, so basically you will have K. So I will write K element would be thickness, cross section area, then gradient stiffness matrix and its transpose, and then stress strain relation matrix, and then gradient matrix. This is for local level. Once you have this local, let's say matrices, local stiffness matrices, then you can assemble, because this would be for K is stand for first element, second element, third, fourth, how many elements you could have. It's based on numerical and the precision you want. Once you have this local matrices, then you can assemble them into global form following this step. Local, compute using this local form, then represent in them into global matrices, displacement field is equal to force, and then apply boundary condition, solve those equation, and then post process in terms of stress strain or principal stresses direction. So in, say, summary of this introductory part, in 2D cases, basically the information would be geometrical information in Lx, Ly, and thickness. Then material data, Young modulus, Poisson's ratio. So you have to find out the displacement, means nodal displacement, elemental stresses and principal stresses, and its respective direction. So how you can deal with 2D problem. 2D problem you can discretize using different types of element. For the sake of simplicity, we will be using the two types of element. One is triangular element and 4-nodal rectangular element. So triangular element is also known as CST, constant strain triangle. In this case, we are using constant strain triangle for just a brief overview. So this was the original geometry. If you discretize this, so basically using triangular elements, element 1, element 2, using anti-clockwise node numbering, you have node 1, node 3, and then node 4, and every node has 2 degrees of freedom because we are dealing with 2 dimension. So displacement in x direction, displacement in y direction, and that can also be denoted as displacement in x direction as u and y direction as v, for the sake of simplicity and correlation with the reference books. Okay, and then the process start from formulation of local stiffness matrix, find out the global one, formulate them into this form, apply the boundary conditions, solve, and post process. So here we looked at how to form the local matrices, because we say 60% of your time will be focusing on this local stiffness matrix. So local stiffness matrix formulated using this formula where we have thickness, area, gradient matrix, which is dependent on element coordinate system, and this element coordinate system I already denoted here. Take one elements, exactly take out one node number 1 or starting point will have 0 0 coordinate, nodal coordinate geometrical coordinate, and then you find out the coordinate of every node. So node 1, node 2, node 3. So basically node 1 can be represented at I, node 2 as j and m. So you have to find xi, yi, then xj, yj, and let's say xm and ym. Okay, once you have this information, you can put into this matrix, gradient matrix, and formula for gradient and the matrices are given here. So basically gradient matrix has area, you already computed, half bh, breadth into height, and then bi, bj and bm, and this I, j, m are 3 nodes. So this bi, bj, bm, gamma I, gamma j and gamma m, these are kind of say explicit formulas relating this information which you already computed, this information. Okay, so you compute T, A, and then gradient matrix, it is B, and then at last you have to find out the D. D is strain relation matrix. So here you have E1 1 minus nu square, nu is Poisson's ratio, and E is Young modulus or elasticity. Okay, so once you have this thickness, area, B matrices, transpose of B, this is transpose, the stress strain matrix B, and you multiply and simplify, then you have element for local element matrix for one element. Once you have local one, you find a respective second and do the post processing. So in the next part we will try to solve a complete problem using this CST constant triangle element and find out some nodal displacement and principal stresses directions.